In this episode of The Bear Roars, Dan Caruso sits down with Ben Bloom, founder and CEO of Atom Computing, for a compelling look into the fast-evolving world of quantum technology. Ben shares how Boulder became a hub for quantum innovation, why neutral atoms are gaining traction, and how Atom's partnership with Microsoft and historic system sale to Denmark mark a major leap forward. They explore quantum's practical potential, from transforming how we design new materials to reshaping global tech competitiveness, and how Atom is delivering breakthrough systems with surprisingly modest infrastructure. Let's poke the bear to kick off the conversation.
Ben Bloom, this is going to be a fascinating talk on one of my favorite topics, which is quantum, and on my other favorite topic, which is portfolio companies, because we are an investor in your company, Atom Computing.
Yeah. I've been in for a while, actually.
In for a while, but not soon enough and not with a big enough check, because I think you are doing extraordinarily well as a company. I think you are doing extraordinarily well as a CEO, and your real talent is as a CTO. One thing we're going to get to in this discussion is when I invested in your company, you weren't the CEO, you were the CTO. And then you became the CEO. I guess once upon a time you were probably originally the CEO.
Yeah.
And then you became CEO again. And at the time I know I was doing a little bit of you're such a strong technical talent, and sometimes a real strong technical talent as a CEO struggles. But from the outside looking in, the progress you guys are making, you're doing a fantastic job, not just as a CTO, but as a CEO as well, and we're going to talk about that.
Sure.
But let's start with a couple data points. One is the most famous CEO, whose name I have to look at because I'm so bad at remembering names. Most famous CEO of today, this era, I guess this isn't true because there's probably two that would fit this category, but Jensen Huang at NVIDIA, the most valuable company in the world. Not too long ago, maybe 6, 9, 7 months ago, he made some statements that said quantum is, 25 years away from doing anything practical, quantum computing in particular. And then most recently, just this past week, Joe Rogan dropped a podcast, and on his podcast was an AI guest by the name of Roman Yampolsky, who has a very credentialed background. And somewhere about 45 minutes into the AI podcast, I've noticed Joe's bringing up quantum more and more in his podcast. I don't think he's done a podcast on quantum yet, although I did, through a friend, suggest a few quantum names, including yours, for him to get on his show. But this guy also gave a negative kind of view of quantum computing. Now, in his case, it didn't sound overly educated, even though he's a very deep scientist. But I could tell by the way he was talking about it. He's not current anyways, but he is credible. And his view was, quantum computing can only do things that a quantum computer can do, which isn't practical and won't be practical. It's kind of like inventing a problem that a quantum computer can solve, and then saying you solved the problem, was kind of a synopsis.
Yeah, so I think there's two things there. So we can go back to Jensen and say, Jensen Huang, I don't even remember the full story of how he got asked this. I think it was a throwaway question. You gave a throwaway answer. And then probably all the people internally at NVIDIA who worked on quantum computing were horrified and whatnot.
Because they're spending a lot of money on quantum computing at NVIDIA.
But they created this like quantum day. So I got a chance to meet Jensen Huang. I got a chance to go and stand up with, I don't even know, it was something like 15 of the other quantum CEOs and go and talk about what we've been building, what's changed in the last few years.
What was the format in which
it was a fireside chat with 10 of your best friends. So it was a big panel where Jensen moderated, and he did like 3 different panels where he moderated CEOs once, CEOs twice, and then he did kind of other hyperscalers. So he had people from Microsoft, and I believe he had someone from Amazon or something like that.
And who else was in the roundtable that you were part of?
I think every single quantum company that has more than, I would say, 50 people and has raised more than like $50 million or something had a person there. And essentially it was everyone telling them like, look, a few years ago, quantum was such a science project, there was no such thing as making money. I think every single person on that stage, one way or another, had made revenue for their company, including Atom Computing. And I think that times are changing. I think that even in the last 18 months, where the technology is just totally insane compared to 18 months ago. 18 months ago, I remember signing up for something with a big corporation, Microsoft, saying we were going to do some technical demos. And I don't know if I'm supposed to go into details about what those technical demos were, but
Sure,
at the end
you
of
got my permission.
but at the end of the day, we went way past what we were supposed to do. And I think it just said that once you have your technology there and all the pieces are together, all of a sudden your systems can outperform what you thought was possible. And I also think this is just generally true across the industry. Like people are now talking about logical qubits, whether they work on trapped ion systems, whether they work on superconducting qubits, or whether they work on neutral atoms. Everyone is talking about qubits that now have some amount of error correction built in, and you're stopped talking about these physical fidelities that people talk about, how good your technology is in a very analog way, and you say, no, let's abstract all that away now and go actually to what people actually cared about, which were fundamentally logical qubits that could do these calculations.
So a couple level setting for the
Yeah.
audience. When we talk about quantum, usually the next word people say is computing, but the better word to say is quantum technology, because there's multiple categories of quantum that are all big. One is quantum sensing, which includes timekeeping. One is quantum communications, quantum networking, which is how do you move information around in the quantum realm. And then there's quantum computing, which is what you're focused on. And quantum computing is the sexiest. It's almost certainly going to be the biggest. It's almost certainly going to be the thing that changes the world the most. But really, when you get quantum computers that are doing what quantum computers are going to do, that will quickly lead to quantum networks and communications, because they got to connect with one another, and they're going to want to connect in the quantum realm, not in the classical realm. And quantum sensors are really kind of like the equivalent of what the Internet of Things is in the classical world. You'll have a quantum Internet of Things where devices of all different shapes, sizes, functions will exist that are collecting and processing information. Think about it at the edge, that they're using kind of quantum to do things that you can't do in classic, but then they've got to be networked together and potentially be communicating with quantum computers. But your focus is quantum computing.
Yeah.
So that's for the audience. And then secondly, when we talk about quantum computing, just to break it down, there's multiple different modalities of quantum computing.
Yeah.
So tell us about the modality that you guys are focused on and how that fits in with maybe, without going into detail about every one of them, but kind of generally speaking, how it fits in with other categories of quantum computing.
So we build neutral atom quantum computers, which is really to say we take naturally occurring systems. These are single neutral atoms. We figure out ways to actually...
And what do you mean by a neutral atom versus, like, are some Republicans, some Democrats?
Yeah, exactly.
Some are neutral?
No. So we have atoms that have no electric charge. So the same number of electrons as they have protons, such that they essentially just don't interact with the outside environment. And that's actually why we use them as qubits. Mm-hmm. They have very, very little interest in the outside environment. And it actually makes it quite difficult to control them. But we've, over the last, I would say, 45 or so years, figured out ways to do that. And there's been a slew of Nobel Prizes and stuff, all kind of based around work that was being done at Bell Labs and MIT and stuff like that. And unfortunately, we just had someone pass away who was considered to be like the grandfather of neutral atoms or something like that, Dan Kleppner. But generally speaking, this technology started a long time ago, mostly looking into how does the fundamentals of quantum mechanics actually kind of control the interactions between particles. And so a lot of the early work was around interactions between particles, because neutral atoms are very, very simple. So supposedly you should be able to very easily write down how they should interact. But of course, like all physics research, you think you know how to write that down. And it turns out to be, even for the simplest systems, really, really complicated. And then 45 years later, there's still people getting PhDs and stuff when 3 atoms come and combine and so on and so forth. But I would say it started and kind of pushing more and more towards quantum sensing. And so the work I did as a grad student now 11 years ago or more when I started my graduate work was all around building quantum clocks. So you had Junyi on your podcast. He was actually my PhD advisor. I worked with him for many years building clocks. And we just got very, very, very good at measuring the energy difference between two energy levels. Now, of course, quantum clocks are really similar to qubits. And this is actually how trapped ions, which is another kinds of qubit modality, started. Trapped ion is like a neutral atom, except you kicked off an electron, so it has a positive charge. And one of the things that these two systems had in common is they have these naturally occurring energy levels, and they have many different naturally occurring energy levels, but you have some that are really, really great at making clocks, and then some that are really, really great at being qubits. And that's how that kind of modality of trapped ions and neutral atoms transitioned from clocks into qubits, is that as more and more technology was being created that has kind of pushed what you can do and how you can manipulate these systems, as it become easier to do that and cheaper to do that, honestly, people just started building more and more of these individually controlled quantum systems. And as you got to more and more qubits, all of a sudden you go from just having arrays of qubits to actually a functional quantum computer.
Let me pause you for a second there, and let's just talk about qubits for a second. So we all know what bits are, ones and zeros. From an abacus to today's most modern GPU, but not including quantum computers, it's always been how fast can you process ones and zeros. But when you use the word qubits, what qubit means is quantum bit. And quantum bit works very different than the world of ones and zeros. And we won't get in that right now, but that's qubits. But when we think about quantum, what we think about is how the world works when things are either very cold or very small.
Yeah.
So when you're using an atom, a neutral atom, as your qubit, how are you making it very cold? Another word for very cold is very motionless. How are you making it behave as something that is, in that realm of being either very cold or very motionless?
Yeah, I mean, I think this goes back to exactly like you said, how do you get it really cold? Because what you essentially want to do is you want to store information inside a qubit, and we can talk about what makes a qubit special. But for us, it's really, you want to have two quantum mechanical levels of energy, and you want to address them. And the way we do this is we find two levels inside an atom. And like most computers, you don't want your information to be kind of just meandering around inside some vacuum cell and go away. You really want it to be locked down and exactly know where it is and what its properties are at any time. So how do you get a cloud of atoms, or any atoms at all, into a cloud? Well, one, you just heat them up and then there's some vapor pressure. And then the other is, okay, you have a huge slew of atoms, like literally tens of millions, hundreds of millions, maybe even billions, bouncing around.
In a very small space.
In a very small space. But the question is, how do you actually get that really localized? And when I say really localized, I'm talking about like 20 nanometers by like 30 nanometers or something like that. So really, really tiny space. Yeah. And the way to do that is, like you said, you cool it down. And now the struggle is that, when we think about cooling and how that works in like everyday life, you usually think about like, for the most part, you usually think about things touching each other such that you have a cold thing and something that wasn't cold, and the cold thing has, enough of a mass or something that it can actually pull heat from the other thing, and they kind of equalize. Now that's not how it works if you have an atom kind of zinging around in some, vacuum chamber or something like that. It doesn't see anything around it. So what you have to do is you have to figure out a way to take that motion, which you honestly don't even know about what that motion is because it's sort of random. That's kind of the nice thing about entropy, or just, don't know if it's nice, but it is what it is. And you need to get it out of the system. And the way you get it out of the system is actually lasers, is actually bouncing photons, which have honestly very, very little momentum compared to an atom, but you bounce many, many photons off those atoms. And you do it in a way such that you kind of always oppose the motion of the atom in any direction, such that no matter where the atom is trying to go, it constantly gets a barrage of stuff hitting it. Like if you could imagine being inside of like a rainstorm, but every direction you went, the rain's like coming towards you. So you do that, and there's lots of weird, complicated tricks about how you go and make things even colder than that. But generally, that gets you down to microkelvin temperatures. And microkelvin is 10 to the minus 6. It's actually, it's 1,000 times colder than you could ever make cold in a dilution refrigerator or something like that. That's superconducting people use. It's an incredibly low temperature where atoms are moving at like I think off the top of my head, I think it's like on the order of like millimeters per second. Even if you just let them go forever, whereas what they're actually doing is they kind of you give some actually trapping potential so that they're still moving a little bit, but they're kind of just sloshing back and forth in their traps.
And what you're really doing, correct me if I'm oversimplifying this, is you're sucking the motion out of the atoms. You're using
Yeah.
the lasers that are precisely tuned with the type of atom you're cooling.
Yeah.
And it just happens that the way physics works is for certain precise frequency, uh, of light relative to the atom, you can basically just take the motion out of it. So when we think of the temperature you're describing, the device that's holding those atoms you could hold in your hand.
Yes, it's really, really tiny. And there's lots of
Yeah.
companies trying to make really, really tiny devices, exactly like you said, for quantum sensing, where, what they care about is making clocks, making sensors. And these systems can be really, really tiny because in some sense, the active elements of these systems are the tiny atoms in the center.
Mhm.
And so everything around it is this classical thing of like, well, I want a little vacuum chamber. Well, how small can I make the vacuum chamber? Can it be 3 millimeters by 3 millimeters, and so on and so forth? So there's been examples where people have created these like chip scale atomic clocks and all this stuff like that. You said something about like quantum mechanical and how it's kind of crazy how you can suck the motion out. The example I would have about that is that like the way we do that is the exact way when a police siren is going past you, and it kind of makes that kind of higher frequency sound as it goes up, and it kind of distorts the sound. It's the exact same thing with the lasers.
Mhm.
As strange as it sounds, the lasers stay at the same frequency, but you've set that frequency such that if an atom is moving towards it, just like in that kind of police siren like analogy, it seems like they're at a higher frequency, and all of a sudden the scattering starts and the rain that's opposing their motion starts in some sense. So it's actually like a very physical process that most people like deal with every day when like they hear sounds, but they don't. It's a little bit funny that special relativity lets this happen at like millimeters per second with an atom.
So what you're doing using the neutral atom approach or methodology, you're using atoms as your qubit.
Yeah,
You're using lasers to
cool them down.
cool them down, take most of the motion, and then we're going to talk about. Then you have to make it such that the atoms can interact with one another in very controlled ways, which we'll come back to in a second. But just in contrast to other modalities, we talked about the trap ion, which is kind of a cousin of that.
Yeah,
Still focuses on kind of a charged atom. Is that the right way to put it? But then there's whole other methods that start to get very different than this method.
And generally, those methods usually, I mean, given the way we just described that, the rest of the other methods usually revolve on the idea that they would say it's hard to control these naturally occurring quantum systems. They have lots of nice properties, like our system can keep quantum information around for minutes at a time. But what they'll say is, what we're great at? We're great at fab. And so they try to create artificial quantum systems, which
By fab, you mean fabrication or
fabrication with
basically-
semiconductors or
basically
with
making artificial.
superconductors.
Yeah.
And so what they do is they try to figure out a way to essentially create a system that's usually, I should say, they're trying to create a system that's anharmonic. And what that means is there's lots of examples in classical physics where you can add more energy to a system, and if you're in a quantum mechanical state, even if you're cold, the system just keeps going up higher and higher in energy levels. And really, that's not ideal for a qubit. In a qubit, you really want a two-state system. You want something that you can say is spin up and something you can say is spin down. If all of a sudden you can go to higher energy levels, you break that assumption, and you have to build different kinds of quantum computers that are even more esoteric and so on and so forth. So most of the time, what people are trying to do is figure out how do you build usually energy levels in some kind of semiconductor system or superconductor system that have a difference in energy between the bottom one and the next one up, and then a wildly different difference in energy between the second one and the third one. And that's all of this kind of complicated schemes for how you actually do that. One of the ones that was essentially pioneered in the early 90s by I think it was by a guy named Nakamura in Japan, was about creating little loops of superconductor. And that is the one that for a long time, I would say, places like Google and IBM have been very, very positive about. And they started putting money into that around the mid 2010s or so, like 2014 or so, 2015. And I think they've done tons of amazing work there, but even those folks are starting to wonder if there's a different future. And part of that different future is about how difficult it has been to actually fabricate those structures in a reliable way. Like people are used to fabricating things that, like you said, work with bits, work with zeros and ones. And I don't think we're actually that amazingly good at fabricating things that are wildly analog in nature and have to be really, really consistently made and really, really clean, honestly. And so what's happened now is that over the past few years, there's been amazing advances in quantum computing across the industry. But even the people who have been working on superconducting qubits are starting to question, I think, what they're doing. I think there's been a lot of just interest in other modalities and even money flowing from some of these hyperscalers to other modalities.
And we'll get to that because one of those hyperscalers is a big partner of yours, and we're going to spend time on that. But talk about photons as an approach.
Yeah, photons are really interesting because it's an entirely different approach. And I think that's also why they're a little harder to grasp how far along they are, because at the end of the day, the quantum computers that you're going to have to build with photonic equipment, and there's some competitors who are working on this, but those quantum computers are just so fundamentally different. They have to speak almost in a different language. And the real trouble comes from the fact that, for the most part, at least in this quantum mechanical way that you want to do interaction between quantum systems, photons do not even interact with other photons. And that creates a really complicated state of affairs where this core piece of what we do in a quantum computer, what we do with matter-based qubits, with artificial qubits or whatever, we create things where we change the energy level that is being occupied by that qubit. We can create a 2-qubit gate, which is really saying we create a correlation between these systems. And those are just it. And we can read out the system, sorry. And that's it. That's the elementary operations of a quantum computer. Unfortunately, like I just said, with photons, they can do something.
Unfortunately for them, not unfortunately
for
your
them,
approach.
yeah. Like they have the ability to have 2 different kinds of states, and there's lots of different ways they've done this, but they have 2 states and they can make changes and rotate between them. They can read out the photons, like whether the photon is there, whether it's H polarized or V polarized, or sometimes they encode it differently. But that interaction just isn't possible. And so they have to build their entire quantum computer around what I would refer to as like a measurement. And so they do this thing where they have different versions of it where they do like measurement-based quantum computing, where they actually take multiple different quantum systems and they make them interact by kind of forcing them some of the time into a state where they were entangled. And there's lots and lots of different ways that they've come up with it. Some really clever, amazing ways to do this. But what that means is that really simple core piece of thing, technology, where you just want to create a correlation between qubit A and qubit B, is actually really, really difficult. And what that means is, to go around this fact, they end up having to create these incredibly, incredibly complicated systems with many, many components, where they are constantly trying to recreate entanglement because they don't have an easy way to just have it on demand. And that is, I think, one of the things that makes it really, really hard to actually compare apples to apples, and also really, really hard when they actually say what they actually want to build, because I think you'll see, there's amazing stuff going on in Chicago or outside of Chicago. There's stuff going on in Australia where there's companies saying we're going to go build photonic quantum computers. One of the things we need is a warehouse and a power plant. I mean, I don't need a warehouse and a power plant for my quantum computer. I think most people don't need a warehouse and a power plant.
You do need a new
a transformer.
Hanging on a power line is that's a different topic.
We want to go to 5 labs to 10 labs or something like that. So I think
Excel Energy, if you're listening to this, we're coming after you guys.
But I think one of the things that we find is that, like, when you don't have this easy way of doing like a core thing, like it's like trying to build a normal computer without an adder. You really have to, scratch your ear by putting your hand over your head or something like that. And it creates this incredibly large scale system that is incredibly difficult, let's say, and very, very power hungry, because you have to have this huge amount of resource state generation and create this entanglement in a way that is pretty crazy. And I think that's the difficulty, I would say, about those systems. Not only is it really difficult to go and fabricate these photonic components and actually meet the specs you need to meet, the end goal looks very, very different than the end goal we're trying to get to.
Yeah. Yet when we look at these different methods of quantum computing, you could come up with examples in each category where the companies who are pursuing them are worth billions of dollars already.
Yeah.
There's that's true. I think with superconductors, it's certainly true with Cyquana and the light. It's true with trapped ions, with IonQ and others, and it's true with neutroatoms. So, do you think that a single modality is going to kind of prevail over the other modalities, or that there's going to be room for multiple modalities when the dust settles 10 years from now?
Yeah, I mean, I think there's the optimistic thing to say, which is yes, but I actually don't know if I'm a total optimist there, because I think that first of all, we should go back to why are they even worth these amount of money, and we can go back to that Roman question. But I think that generally speaking, compute is won by dollars per compute, and I think that there's right now many different platforms you can pay for, on AWS, with different dollars per compute level. But they're mostly all based around the same technology. And so I think, the company that's going to have the cheapest dollar per compute is probably going to be the company that wins. And I think it's going to be a race both to utility scale and a race both to how cheaply you can get your computation done, how cheaply and how quickly. I think that one of the things we'll find, and this is something we've spent a lot of time thinking about, is first of all, how do you make the computation faster? And we spent tons and tons of time thinking about that. But even after you get that and we say, look, this is great, now we know how to do this in the absolute fastest way possible with our modality, there's always going to be a question of, okay, but now say we're 20 years from now, or it doesn't even have to be 20 years, we're 5 years from now, and someone's doing a really complicated calculation. What if we had just built twice as many systems? Like, what could they have done? Could they have done that calculation in half the time? Could they have done it in a quarter of the time? And I think that is a whole other scale where I think once you get into this stride of being able to access some of these, what I call utility scale calculations, it all is going to be a question about how many dollars did it take to get you that answer, and how many dollars either per compute or dollars per time. Like if someone says, look, I'd pay 5 times more to have that computation done in 3 hours instead of 6 hours, we're probably going to want to figure out how to do that. And I think that's a big part of, at the end, who's going to win is the company or the technology at the end that can deliver these things at the cheapest price and at the fastest time. That's what's going to matter.
Yeah, but in some respect, if you say, well, who's won the computer race before quantum? What modality won that computer race? You say, well, what modality won that race when and where? Are you talking about who was winning in the 1970s or the 1980s or 1990s or today? And then you say, where? Are you talking about like a major, data center environment? Or are you talking about, your personal computer? Or are you talking about some really small device that acts as a computer on your bike?
Yeah.
So I think the question of modality is maybe more,
nuanced.
It's like more nuanced. It's like, not every modality is going to win. Not every modality is going to prove to be successful. But, if you fast forward 40 years from now and quantum technology is proliferated everywhere, there's probably elements of what came out of what trapped ions is doing that found its way somewhere, and certainly neutroatom, and maybe superconductor finds a role somewhere in there, and maybe the Cyquana light-based photon-based approach finds its way.
Yeah, I mean, I think it's probably true to some extent. I think that at the end of the day, though, I think that what's going to make that all possible is applications. And it goes back to that earlier question of like, what are quantum computers going to be good at? Because I think the more value quantum computers can give to customers, can give to society, or whatever you want to call it, I think then, yeah, you're right. There's going to be more and more uses on the edge, more and more uses at different scales and different sizes, at different price points even. And maybe that will flourish. But I think it goes back to the uses. And I think one of the challenges, I think, for most people when they look at quantum computing versus classical computing is that I generally now think of classical computers as almost like big data machines. Like you have lots of really, really simple calculations. You have lots of data flowing in, and you have lots of things calculating these really, really simple things. And I also now think of quantum computers, having thought a lot about applications over the last few years, as something just fundamentally different, which is big compute.
Yeah.
And
Well, when ChatGPT hears
Yeah.
what you just said, it's going to be very upset that you called it just a simple processing machine, and it's going to like come out and get you. So you better be on the lookout for what today's AI is going to do when you just critique that. But what you mean there, to take a little bit of the joking aside, what you mean there is even the most advanced AI today, and the approach for AI today is really just doing what computers have always done. Now it's maybe taking it a step further in the software approach, where they've been able to do it such that the AI is really just taking advantage of huge data sets of information and sort of predicting what's the next thing that that can be inferred by the question you asked or the problem you asked it to solve. And so the most probable right answer for that was the word and afterward and was red, and then the most probable one was or blue. So it's just kind of it's almost in some ways a much more powerful than what Google search has been, but it's all just based on taking all available information and making a really, really, really good guess as to what's the most likely best word to fit in next, and then next, and then next. Versus quantum computing is just fundamentally different than that. Quantum computing is not just taking a similar approach with a different type of machinery. It's taking a different approach altogether to how you solve a problem. Can you talk a little bit about what that means?
I mean, I think fundamentally, I think at the base, let me go back to that comment you made about Roman, which is that quantum computers are going to be good at what quantum computers are good at. Or maybe
he was saying in a much more dismissive way.
Oh.
He was even saying in a dismissive way that that you almost have to define
the problem.
The problem such that the computer can solve it. But when you do that, the problem isn't a real problem, and no one cares about the answer anyways.
Oh yeah, I would take it. I would take it a step closer to. I wouldn't go infinitely far from what he said, which is I would say, quantum computers are going to be good at the things quantum computers are going to be good at, and that isn't everything. And I mean, for better or worse, I'll have to live with that.
But it is real things that matter.
Yeah.
And that's the difference between what he was saying. He was saying they wouldn't be solving anything that really matters to us in the real world anytime in the many decade future.
Yeah, I mean, I don't.
And
really
he was sounding
that.
ignorant, to be honest with you. But talk about what kind of real world problems, can't be addressed by classical computers, but are well suited for quantum, and why they matter.
Yeah. So I mean, there's always like two different ways to go about this, and I think the way we've looked at it is, and especially we've done this for government grants and contracts and things like that, is we've really focused on things where we know there's what they call like a provable exponential advantage. So something that we're just unquestionably certain is just never going to be able to run on a classical computer. Now, there's lots of really amazing things that people have been working on, I would say, ever since quantum became a thing in industry, on heuristics and optimization and all these things that people have been building, which really might actually have a lot of promise for even industrial problems, even potentially nearer term than what I'm discussing. But I don't think you can write down on a piece of paper exactly why a classical computer can't do them. And so I think there's always going to be questions of, is it actually better, faster, cheaper? Now, what I think of as the big problems we want to solve on quantum computers, it's again this like materials and chemistry modeling. And the reason why I say this is that we use a huge amount of power in the world on building things, on actually building unique ingredients to life, like fertilizer and things like that. And that's just one example where we have a chemical process it's been built up over many, many years, hundreds, but like tens and tens of years.
Dozens of years, yeah.
And we understand pieces of it, but we don't understand all of it. And we don't understand, can we make that process actually more efficient? And there are companies, though I've learned that they're not exactly the companies we have, in the top of our minds, like DuPont or something like that. But there are companies who are entirely focused on how do you make catalysts? And how do you make catalysts cheaper And then how do you sell
What
that?
do you mean
to
by catalyst?
like something that starts a chemical reaction or kind of moves something from one end of a chemical reaction to the other. But I think that there.
Well, let me pause you there again. Like from one end of chemical reaction to other, what does that mean?
Well, I mean, I think that when you want to actually do this nitrogen fixation, when you actually are going to put an extra nitrogen into these chemical compounds, you have to drive that some way. And the way we do that is a lot of heat, a lot of pressure also, and also kind of a piece that's like an intermediary called a catalyst.
So you're trying to create a material that has special properties.
Yeah.
And that happens everywhere. It happens in building. It happens in
and I think
fertilizing.
the materials ideas are similar to that, where you talk about like, well, you want materials that are, I mean, light and strong, and if you can find different kinds of materials, exactly.
And sturdy.
And it's
but
kind
also
of
but in the drugs, you want a drug to do certain things and not do other things. So you want a battery to have certain characteristics and maybe not other characteristics. So throughout the spectrum of whether it's molecules for drug research, for creating drugs, or it's materials for space or for buildings or for food. We're constantly in a quest of finding kind of a magical set of ingredients to create something that doesn't exist naturally and can be reproduced cheaply and at scale.
Yeah, I mean, there's the examples you just gave that are, I think of there's examples that will actually end up being, the giant, industrial engines that power by money all of the amount of compute for quantum compute. I also think there are these existentially amazing things we could potentially do if we understood high temperature superconductivity and things like that. So you can look at materials that we have now.
So pause there for a second. Like, what do you mean by that? If we could understand high temperature superconductivity, you could do amazing things. What kind of amazing things is it creating?
Oh, like maglev trains and transmitting power without losing power across lines and things like that. Like things that we just take for granted in our society are all based off of Ohm's law and the idea that you're going to drop some voltage across some wire. For a long period of time, most tabletop science done in America, I would say, for condensed matter, for even AMO physics, has all been kind of meandering around the question of, is there a way to actually make a high temperature superconductor? And when they say high temperature, they don't mean hot. They just mean room temperature. Like literally, could you have a superconductor outside on a pole, like a power line pole, instead of having to put it under, like some impossible amount of pressure or have to cool down to minus 200 degrees Kelvin or sorry, minus 200 degrees Celsius, sorry about that, or something like that. So I think that there's the things that will, I think, be the real drivers of.
Let me pause you one more time just to put in maybe a little bit of perspective for people listening in. Is we have this kind of big tension that is existential, and that is we as a human race are consuming more and more energy, which is extracting from our home here on Earth, extracting kind of what is valuable here and is causing Earth damage. And a lot of people are concerned, rightfully, on what we're doing to our environment. Yet, if we want to preserve our environment using only today's methods, that means we almost have to stop society from advancing. There is no AI. In fact, we don't want people moving from being hunters and gatherers in poor areas into cities, because then they consume more and stop getting on airplanes and all that stuff. The only way to control it without technology advance is slowing down society advancement.
Or bring back nuclear power, as some of our big hyperscalers are trying to do.
Yeah. But what you're one way to think about everything that you're talking about is continuing like a whole new level of advancement.
Yeah.
But at the same time, doing in ways that you're not consuming energy. It's not a trade-off of costing the planet, valuable resource at the same pace or cadence, while still creating, things that us as advancing humankind are going to want to create.
Yeah, I mean, I think quantum computing really hits both of these. It really hits these big challenges where we think we know exactly what we want to do to create, these easy methods like high temperature superconductivity, but at the same time, I would say just even slight advances in materials, have a huge benefit to society. And I think that's actually going to be where a lot of money is made on quantum computing, is people just asking these questions of like, are there ways to make this material lighter? Are there ways to make this material stronger? And instead of trying to go into a lab and try to build material after material after material, instead use simulation. I mean, this is the change of simulation on anyone's laptop or simulation in HPC. Like all of these different kinds of jobs that exist now use computers to do simulation. If you're an architect now, you probably use a CAD program or something like that. And it's not exactly the same, but you build probably in some ways, tens of thousands of different kinds of buildings on your computer. Mm-hmm. And then you actually go and build the building you want on the first try because you were able to use that computer and optimize this and say, connect this to here and so on and so forth.
But why can't Gen AI do this? And why do you need a quantum computer to do this? Why can't you just keep advancing Gen AI and do what you described?
I think it goes back to, at the end of the day, the challenge is it's hard to do these things because once you get to the small scale, once you try to look at materials, there are ways of doing normal HPC simulations that get you closer and closer to the answer, but they don't get you all the way. And as soon as something, honestly, very quantum mechanical happens, they're very unlikely to get you all of the way. And that's actually one of the things that quantum computers are very good at, which is exploring these things where quantum mechanics is critical. And I would say normally if quantum mechanics isn't critical, we probably have a classical theory that can do the simulation and so on and so forth. But Gen AI is only as good as the training set it has, and also the understanding of how to take a calculation and actually bring it all the way to the answer. And it's not anything but a classical computer. Like at the end of the day, Gen AI is still a classical computer. So even if you can write down the equations and you tell whatever agentic chatbot or whatever you're using to say, go solve this equation for me, it's just a classical computer. So it can only ever do as well as a classical computer. And for some examples, it's just a question of how much data is actually in the problem, how many correlations are in your system that you just can't track on a classical computer because you just don't have enough bits. And so there's this extra special property of qubits that essentially the complexity of data that can be stored is like unimaginable. Like people talk about how many logical qubits or how many qubits that are perfect you need to describe different aspects of a system versus how many atoms are in the known universe. And very, very quickly you get into these numbers where you can have what I would consider to be a small number of logical qubits all of a sudden storing more information than the number of atoms in the known universe. And that's just not something a chatbot or Gen AI is going to be able to overcome. Now, I will say I don't want to be too dismissive of AI because I think AI is actually going to be critical in.
That's because you're worried it's going to hear you.
Yeah, exactly. Get you. Yeah, I always say thank you, though I'm told that wastes extra time or money or whatever. But I do think that it's actually going to be critical in understanding how to use compute effectively. And so I don't want to say actually anything negative about AI because I think it's
they're going to feed off each other. AI and quantum are two different things that are going to compete with one another.
Yeah.
They're symbiotic technologies that are going to work with one another.
Yeah, and I think the example I have right now in my head is that we're on the brink of something where we have lots of different compute modalities, like not even including the one I work on, which is quantum. We have, for example, just CPUs and GPUs. And right now, most of the decisions about what parts of a problem get run in some algorithm on a CPU and what parts of the problem get run on a GPU is right now decided by a human. And that's obviously not the right thing to do. What it should really be is like, well, actually, it costs this much to run on a CPU. It costs this much to run on a GPU. Just go figure out what is the cheapest way for me to get my answer. And I actually do think we're at the cusp of that. Like, I think AI right now in the next, I don't even know, months, year, will be able to figure out, with different APIs and different interfaces, actually, when someone gives me this hard problem, I send this piece to this computational unit, this piece to this computational unit. The answers come back, I combine them, and all of a sudden, for a cheaper amount of money, I was able to figure out what mix to run on CPU, what mix to run on GPU. I think a few years from now, as there's more and more modalities of computing, including quantum processing unit, I think quantum processing units are going to fit into that same thing. I think what gets run on a quantum computer is actually going to be decided not by a human hand tuning a complicated algorithm, but I think really soon it's going to get decided by AI. It's going to get said, it's going to understand that this part of the problem is quantum mechanical. This part of the problem is good on a GPU. This part of our problem is good on a CPU, and it's going to attribute that.
Yep. So let's talk a little bit about the word quantum advantage and the word quantum supremacy, or the expressions. What at a high level do those mean? Not how they were originally measured, but what do they mean? Like when you use the word quantum supremacy or quantum advantage, what does that mean to you in this day and age?
So I think quantum supremacy, I think people use different terms, but generally when people talk about quantum supremacy, they do talk about something that's solvable on a quantum computer that is impossible or somehow is outperforming all classical computers. But it doesn't really say anything about if it's useful or not. And that really gets at that problem that that interviewer had mentioned, which is that, it doesn't really matter. Like if quantum computers can output a set of random strings in a different distribution than a normal random string distribution, I don't know if that actually changes or affects my life. Quantum advantage, I think, is a slightly more squishy term, but it really goes back to better, faster, cheaper. Like, did a quantum computer do something better, faster, or cheaper than a known a known classical solution? And I do think that's important, because I think that if you do solve something better, faster, cheaper, then obviously if that's worthwhile to the person who's trying to solve something, they should keep doing that, and they should put money into that amazing flywheel, and quantum computers will get better and better and better. Now I think there's something beyond that, which I think even the US government has, maybe they came up with the definition, which is utility scale, which is very clearly trying to state something that really is better, faster, cheaper, but on a scale that is, I would say, making the value of solution also large. And I think that's the key part, where
economically significant, economically material.
Yeah, like if you spent $100,000 on this calculation, because it costs this much energy to run, this much time and effort to build these systems, and so on and so forth, at the end of the day, there better have been something worth, $1 million coming out of that solution. And so I do think that utility scale definition is probably the one that most people are honestly pretty excited about. And I would say, the government put out this, call saying, everyone who thinks that they have utility scale quantum computing by 2033, raise your hands. And, even they said, everyone got to go and talk to the government about this. And they picked 18 companies and said, wow, okay, you 18 companies, figure out a way to prove us wrong and prove that by 2033, you're going to have utility scale. And I think that those companies were across the United States and a few international companies as well. But I generally think many people raised their hands, and the government wasn't able to say no to all of them. Like, I think more than 18 companies raised their hand. But the government, I think, also could only take in so many. So
were you one of them?
Yeah, we are one of them. Yeah. And I think we're working pretty closely with that team, and it's a combination of understanding not just how the hardware scales, not just how you control the system, how you build the system. It's also about the algorithms and about the value of what you're actually returning. Yep. So if it costs $100,000 in your claim to go run this many times, to go do this, that, and the other thing, again, that problem has to come back and be worth way more than $100,000.
Right. So when do you think a quantum computer that you're building will be able to do things that matter, do things that you can't do on a classical computer, or maybe you can, but you can do it far cheaper, quicker, faster, and that it's a meaningful real world application?
Yeah, I think the answer is 2030. I know that's not the greatest answer, because people always want it to be tomorrow. But I think going through roadmap after roadmap after roadmap exercise with people internal at Atom, I think the answer is 2030. I think at 2030, there will be modules of an Atom computing system that will literally just displace HPC being spent on by a variety of researchers at national labs at various places in the US, and I'm sure abroad as well. that are all focused on materials research. Because I think one unit of compute, that the one that we will sell in 2030, can just do that. It can just absolutely displace money, like HPC compute that they're doing now. Like they have a budget, they have a number, and they say, this is how much we spend per year. We do this, that, and the other simulation. And in our roadmaps, we're like, well, we can beat that for a cheaper price.
Yep.
So
we alluded to earlier a hyperscaler that you're working with. Tell us what you could tell us about who that is, how you're working with them, why the two of you are working together. Is it a unique relationship? I'm not saying exclusive, but is a unique relationship, and in what way is a unique relationship?
Yeah, I mean, so we were approached by Microsoft the end of 2023 because of all the advances we'd had, both at Atom Computing with our neutral atom quantum computers, but also in academia. There was just an amazing set of new results coming out that really showed the power of what you could do with neutral atoms. So we got approached by Microsoft. We worked with them for all of 2024. And when we ended 2024, we demonstrated taking our system of this time a few hundred qubits, making about 50 or so, actually almost 64 logical qubits, and then starting to do things with those logical qubits. I think what we showed is we could make really high fidelity entangled states with 24 logical qubits, and we could do algorithms with 28 logical qubits. And then we just ran out of time, and it was Microsoft Ignite, so we published. But I think that generally speaking with them, I mean, it's been a combination of technology exploration and development. So we work with them on near-term demonstrations. We work with them on understanding how their algorithms and error corrections will work in the far term, because there's more and more complex quantum error correction that we want to do with them. And then what's been recently changed is, and this got announced by Satya Nadella, is we have a commercial partnership with them.
So it got announced by the CEO of
so it got announced by the CEO at the end of November 2024 at their internal Microsoft Ignite conference, that we are going out and have a system that is a co-designed system. So it is co-designed by Microsoft and Atom Computing to implement Microsoft's quantum error correction protocols. And that with that system, we're going to deploy it at different customer sites. And so what will get announced on the 17th, which, this won't come out until after the 17th.
We'll make sure that.
Is that we've made our first sale now. And so this first co-designed system is going to Copenhagen and was purchased by IFO, which is like the state of Denmark, the sovereign wealth fund there, and the Novo Nordisk Foundation, which, famously owns Novo Nordisk and things like that. So this is a system that will push the bounds of what you could possibly do on a quantum computer by every stretch of the imagination. And as I would say, one of the biggest system sales ever in the world, certainly the biggest neutral atom system sale, and just generally is meant to drive a ecosystem of companies to exist in, I was going to say Copenhagen, but in Denmark and other Nordic countries. So this is actually a combination of Norway, Sweden, Finland, and Denmark.
And the idea there, because you were sharing this with me a few days ago, the idea there is if what they want to do is they want to spur their quantum economy.
Yeah.
And if you spur your quantum economy, it's not just about the quantum computer, it's about all of the applications that get built on a computer, the companies that are created to build those applications, what comes out of those applications, unique materials, unique drugs. So
it's like venture capital for the public world. I mean, they want to make sure that if there's applications for quantum computers, that those applications are owned by companies that already exist in Denmark or the Nordic countries. I have to keep saying that. Or they want to make sure that companies that are formed around quantum computers are built in Denmark. That there's a kind of central location that will make that benefit for that country or for that few countries. I mean, I think you can kind of imagine it again as like venture capital on a kind of national scale, which is that if they can put a little bit of money now and start these things,
a little bit of money to them, but a lot of money to you.
It's true. It's a lot of money to me, but a very little bit of money on a national scale. And I think their hope is, one of these companies might have a new drug. One of these companies might create a new material or create a new way of designing materials. And that is worth a huge amount of money. And what they want to do is they have different programs working on their own versions of how they want to build quantum computers. They have, their own academic research. And what they said is like they need a system right now. And that system right now is going to allow people to play with quantum computers right now. And that's what they want.
And in some respects, you're shipping a system to them. In other respects, that system's coming with an ongoing service package.
Yeah.
So describe what that means. Like physically,
Yeah.
what would you be delivering to them? What would it sort of look like? What would be the physical characteristics? But then what are you going to do with them in partnership and with partnership with Microsoft? Because this was a joint sale with Microsoft.
Yeah.
What is the combination of you Microsoft going to do along with the physical system itself to deliver the service?
Well, there's the super boring stuff, which is, we send people and hire people there to make sure that after we build the system there, it mostly gets built in Colorado. We ship over pieces, we rebuild it, blah, blah, blah. And then once it's up, we just want to keep it running. So there's the few people whose job it is to keep it running. If a laser breaks, they get on the phone with the vendor and say, why is the laser broken? And so on and so forth. But I generally think we're also going to be building, like I said, or like you said with Microsoft and others, we want to make sure that they are getting the most out of that system possible. So I think there will be applications engineers, there'll be error correction theorists, there'll be researchers there to partner with all the people who are going to be lined up to use that system so that they can get the most out of their time on that system. And it's not, again, just Atom Computing folks. It's like you said, Microsoft folks. So Microsoft is committing to have those same people there, have the same amount of handholding. But at the same time, Microsoft is also building on top of the system. And that's actually another cool aspect about this, which is we're selling a quantum computer. You can use that quantum computer by sending really low-level commands to it. But Microsoft is working on error correction on that system so that they're working how to abstract the neutral atoms away so that no one ever cares that it's a neutral atom quantum computer, except for me. And that also...
And me.
And you, yeah. And also that there's applications on top of it. That there is Microsoft APIs and applications so that when you run on this system, you can actually access it in a fundamentally different way where you are trying to probe the actual things you want to do, trying to probe some of the models you want to run on the quantum computer, and you're not stuck in this kind of super low level language, which everyone at Atom constantly lives with. But we want our customers to be way up leveled than that. Like, most people don't program in machine code. I'm sure there's some people outside of the companies that do, outside of Intel and NVIDIA that do, but most people don't. So leave the machine code to us and others can go higher up in the stack, essentially.
Yeah, so it seemed like overnight we went from most of us never using the word Gen AI to everyone having Gen AI on their quote unquote laptop and having the full power of ChatGPT at their fingertips. All about the same time. Yeah. Maybe there was months difference, but there wasn't. But we all had access to the power of it in a pretty complete way pretty quickly. But what you just described is different than that. What you described is in order for the Nordics to create an advantage for their economy, they're going to have brought to them this physical early form of quantum computer and a support team around it so that they have unique and exclusive access. In fact, they even will gatekeep who within there has access to it, and in the hopes and in the expectation that that's going to give them a huge outsized advantage in creating businesses,
attracting talent,
and discovering things that haven't yet been discovered that are very valuable. That's a paradigm difference, and one that I think hasn't really been absorbed. There's going to be a period of time measured in years because that quantum computer you deliver there is not going to be the same quantum computer that you would deliver 2 years or 3 years later, maybe to them, maybe that one goes somewhere else. But you're going to have this time period in years where who has access to what quantum computing resource can potentially do things that no one else could even do even if they were smart enough to do it.
Yeah.
What do you think that means? I mean, to me, I can't think of an analogy to that in recent memory.
I do think there's an analogy, which is access to GPUs. I think that access to GPUs is highly controlled at various points in time, but also like access to a large number in a specific place, all networked together, that is pushing AI forward for some folks and not for others. and entire companies have been built around the idea of, in some sense, democratizing it. I don't want to say democratizing it, but creating an industry where if you're not a Microsoft who can buy some impossible number of NVIDIA GPUs, you have to go to a CoreWeave or something like that, so that you can have access to these large numbers of systems. And it's just like that, which is there's even fewer, I would say, really amazing quantum computers in the world. And I think it's going to be a scarce resource for a long time. Now, I think there's also going to be interesting examples where I think other countries are going to go along this path where they bring in this same kind of path where they go and they purchase systems and they try to build stuff around it. But I think that this hand-in-hand, connection with both if you want to call Microsoft an applications company, as well as a hardware company like Atom Computing coming in together, I think that's pretty unique.
Yep. And do you expect to sell? This is your first kind of large scale sale. Do you expect to have other?
I think we'll have more news coming soon. I think this is a new and emerging market. I don't think that this is the long term of what quantum computing looks like. I think the long term of what quantum computing looks a lot like what classical computing looks like, which is you access via the cloud, and there's giant cloud data centers and so on and so forth, many quantum computers, and we Atom control how that gets accessed and so on and so forth. But I think right now, a scarce resource there people can build stuff around is what people want. I don't know if they want it to be scarce, but certainly it's what exists right now.
Well, it is scarce. They want access to it. Yeah. And I imagine there's going to be, not unlike right now, an example of Microsoft and the NVIDIA GPUs. Yeah. There's going to be companies who want to have unique access to kind of the state-of-the-art quantum computers early on, so that they can, some of them will be established companies, and some might be the equivalent of OpenAI, where it's a new company that comes out of nowhere and becomes a very dominant company because they learned how to get both access to the right quantum computers and learn how to use it to do very special things before others have, and all of a sudden they're worth
I think that is the playbook of this Nordic deal, which is that they believe, what are the chances that they have OpenAI, the new kind of quantum OpenAI, formed in Denmark? That is what they're doing. They're saying there's a chance that that's possible, and just like a venture capitalist, they're like, yeah, we put in what for a government is a tiny amount of money, and then there's a chance that the next one is in Denmark.
Yep. And which has got to be hard because they're betting on both the modality, right? So they're betting on, by working with you, they're betting on a modality, and then they're betting on a specific company in that modality, because you're not the only one. There's not that many scaling quantum computing companies that do neutral atom, but you're not the only one. You're one of maybe 4 or 5 that are material.
But I think in terms of, and if I look at it from the customer's perspective, first of all, I'm glad they picked us. I think there's lots of amazing stuff we're doing right now. I think we're steps ahead of others. But if I look at it from their side, I don't think they exactly are saying, oh, we're picking this modality forever. I think they're saying,
but they have to pick it.
They had to pick it now. Yeah, they had to pick it now. They had to make a commitment now. But I think the way they're creating this entity and the way they're approaching this, I think every 2 or 3 years they're going to purchase a quantum computer. Yeah. And I think that they are going to do that so that, again, their focus is on building companies around applications and so on. They have, Novo Nordisk Foundation funds a ton of research into their own quantum computing hardware efforts. It's probably the case I don't want to say anything too negative, but I think they're a ways away from having an operational quantum computer right now. They could say that and they wouldn't argue. And so they're thinking, look, we can build the applications now on systems that exist now. They bought the Atom computing system. I bet they'll buy other systems in the next few years. And they're just going to keep building that IP and that knowledge in the area, and hopefully a vibrant ecosystem of companies. And it doesn't even have to be new companies, by the way. I think there's lots of other interest in Denmark by I would say big industry around how do you use these quantum computing systems and how can you get access to this system. So.
Yeah, how do you get access? That's I think going to be something people start to talk about more. I don't think that full realization has kind of hit the broader marketplace. Other geographies who you think are going to take similar approaches whether it's with you or someone else?
I mean, I think there's places in Asia. I think there's places in the Middle East. I think there's already some examples where cheaper versions of this and smaller versions that I don't think are necessarily pushing the envelope of what you can do with a quantum computer, but have already existed throughout the Eurozone. I mean, I think this is actually a pretty common strategy outside of the US, honestly. I think that, yeah, I haven't seen anything too much beside that. Oh, maybe there's more stuff in Asia, actually. So there's many examples in Asia, I think, where this is actually happening.
Yeah. Yeah, no, we read about all the different countries who
Yeah.
are investing, and I think what's unique is looking past the quantum computer into the quantum ecosystem.
Yeah.
I think that's maybe a new realization that is coming to be that, that you don't have to win the quantum computer race as a geography or even as a company, but you're not going to want to lose out on the quantum ecosystem race,
Yeah.
because that would be a whole different thing to fall behind on.
I mean, I think the challenge for atom computing will at the end be, if we're successful, is how do we become more vertical, so that we get a piece of that application space as well. But I also could see it from the outside perspective, which is, most of the value of computing has been reaped not by Intel. I mean, they're an amazing company, huge valuation, or not huge anymore.
Not huge anymore.
But
certainly at their peak.
But like, you can go back and say, well, who actually made the most money? It's going to be all these people who built on top of it. And I think that's going to be, I think, also happening in quantum computing, which is that the value is in the applications. And I think that, we want to atom computing, make sure quantum computers exist. We want to then try to get up higher and higher and more vertical, so that we're eating into that as well. But it's true. I think
I think it's an end question, because Apple was a hardware company, still is in many ways, and NVIDIA, would you call them a software company? To some degree, maybe, but they're certainly a hardware company. So I think there's multiple spots in the value chain where the winner is going to be very successful. You don't have to be at the application layer to win. You don't have to be at the hardware layer to win. You could lose everywhere as well.
So. Hopefully not.
So let's get back to physically. What does this version of your
what does it
quantum
look
computer
like?
look like?
Sorry.
And what environment does it need to sit in?
It needs to work in an environment with working air conditioning. That's going to be the biggest thing that is, I would say, not an impediment, but I mean, our systems, we've built them in converted office buildings, and what we do to make it possible is we add a nice air conditioning unit. That's it.
That's a big deal, what you just said there, because you contrast that to today's kind of AI clusters. I mean,
there's like
we got to build nuclear power plants. Is what we're talking about. But what you're saying is, hey, we've got a early functional quantum computer that we're going to be shipping and deploying, and the environment it sits in is not an outlandish.
It's like, I mean, what we're looking at now, and we talk about site selection and stuff for where we're putting this. We pretty much say, look, we need one room and a nice air conditioner. If you think about what is
how big of a room?
Yeah, so I don't remember the exact size, but it's like 20 feet by like 30 feet, or maybe it's even less than that, like 20 feet by 20 feet or something like that. So it's not a particularly large room. And inside that room, there's something like 4 or 5 19-inch racks. And then we use an optical table. So it's some space where we move in a giant piece of metal that just gets rid of vibrations from the floor. And that's something like 4 feet by 6 feet or something like that. But so it's the 19-inch racks and that table, and that's kind of it. And there's a bunch of equipment on that table.
Yeah. and as you look out, 5 years from now, what does the form factor change?
Yeah, I mean, I think for us, it's all about the 19-inch racks stay about the same. So we have lots of plans about how to get the racks smaller, so there's just fewer 19-inch racks per what we call module. And then the system itself, actually, like I said, we do these things in neutral atoms inside this, I think I said, a vacuum chamber. Vacuum chamber is already pretty small. We might want to make it a little smaller, but it's actually quite small. And the rest of what we do is all about creating microscope objectives and then having images go into the back of the microscope objectives, because essentially all the manipulation is done with light. And so we talked to, and I just talked to today, companies that make, in some sense, high-end projection equipment or commodity projection equipment, and figure out how do you actually create lots of spots of light and then how do you have control over each one of those individual spots of light. So the system kind of keeps getting smaller with each generation, because we just hire more engineers instead of physicists, and then B, because the system actually does get a little simpler with each step. Like, we kind of understand what are the bells and whistles we actually need versus what are the bells and whistles we can live without. And then with that, we just keep making the system more integrated and smaller. We don't try to get it to be like, fit in the back of your pocket, but we imagine that on that same kind of scale, we would want to fit on the order of like 4 to 6 systems. And then when we start talking about, giant clusters of these things, we're actually not even talking about that many. We're talking about on the order of 8 or 10 of these things together create what I would call is like a universal quantum supercomputer. And I think, if you want to do some problem that requires somehow way more than the things we've already talked about, it's, well, you hook, instead of 10 of these together, you hook 20 of these together or something like that.
Gotcha. And let's go off on a little bit of a tangent and talk about the origin story of atom computing and kind of how you got it started, how you founded it. And then we kind of glossed over in the conversation where you're really at as a company. I mean, we glossed over and got to like, a big sale, a big partnership, but maybe we'll start with, when did you start this? Where did you start it? Was it just you at that time? And how did you, why were you qualified to start it? You mentioned kind of, CU Boulder. I think you were at NIST as well. Is that right? Or,
I was actually
really
at
Gilla. Gilla, which is a partnership between NIST and CU Boulder. So, give us a little bit of your origin story.
Yeah. So, I mean, so let's just go way back. So I did my PhD, like I said, at Gilla. Afterwards, quantum just...
Maybe while you mentioned Gilla, why is Boulder a hotspot for quantum?
Oh, yeah. I think it's actually a really great question. I've always struggled to answer it. So I kind of go back to this idea that NIST was first put in Boulder. So there was a entire institute that was somehow meandered its way into doing quantum research. And that quantum research really kicked off in the control of individual quantum systems.
And that was when this started?
That's a great question. I forget.
But like 70s? So
I think so.
Not recently.
No.
Decades ago.
Yeah, but it started there. And I think, like I said, they meandered into this research of clocks. And then they've meandered from clocks to like individual trapped ions. And then they also were doing some of the pioneering work in superconducting qubits. So just the control of individual quantum systems was really a big focus of NIST in Boulder for a very, very long time. And at the same time, Jan Hall, started actually Gilla and lots of folks were involved too, essentially forming a partnership between CU Boulder, which is in the area, only a few miles away, and NIST. And all of a sudden that created this complicated thing where you had institutes that were working on quantum mechanics at the CU physics department, now at this new thing called Gilla, and at NIST. And I think it just kind of blossomed from there, just essentially more and more talent coming to the area, and then just companies starting to form from that. And I mean, that's just generally how things work, I would say, is that, you go and you do research, and then, some of that research you think, wow, shouldn't this be something everyone can access, and you go form a company.
Mm-hmm.
And that's, I would say, how most things just turn out with government grants and things like that, is they kind of spool into these companies. And I think Colorado just had that right mix. I know that sounds really dumb that I'm saying like, oh, there just happen to be a lot of people, but that is kind of how things happen, and it is the way. So I was here until 2014. And then afterwards, I will say, it's not that quantum mechanics didn't exist or quantum computers, didn't exist at that point, but in my mind, there was no commercial interest in quantum computers at that point. And I really wanted to go work on something that was big and had like impact to everyone. And I actually went to Intel. So I was at Intel for a few years, and I worked on, at that time, it was 10 nanometer, which at that time was far flung in the future, let's say. And it was interesting. I got to see, at that time, like I think Intel was like 120,000 people or something like that. And I wasn't working in like production, but I was working in like, I think you'd call it development. So it wasn't quite research, but it was like development. And it was interesting. I got to see how, huge numbers of people working together could build really, really complicated stuff. But at the same time, like, it also didn't scratch the itch I had for more sciencey stuff and for kind of really cutting edge research. Because at the end of the day, I think I joked with people is that, like, most of my job was like, well, how do we create these rectangles better? And it was like, it was kind of interesting. And like I said, I learned a lot about fabrication and learned a lot about lots of people and trying to interact with lots of people and coordinate the efforts of lots of people. But the challenge was rectangles. And I was like, well, I don't know. So after that, I was like, I really want to do something, much more researchy and much more hardcore. I still love compute and so on. But I went and actually joined Rigetti. So I was one of the first like 20 employees.
Yeah, and Rigetti's an early quantum company, but that was worth.
Now it's
probably worth a lot of billions of dollars for whatever reason.
Though they've had their ups and downs.
Yes.
But regardless of that, I think that when I joined, it was really tiny. I look back at it now because I've gone through the entire cycle with Atom Computing, starting with way less than 20 people. But when I joined with 20 people, I would say they grew a little bit faster than Atom Computing. I showed up and there was lots of really cool stuff happening. Maybe slightly less than I thought was going to be happening at that point. But at the same time, the thing I saw there was that 20 people, 30 people working on a problem got so much done so quickly. And I was just flabbergasted. And that wasn't the case of what I saw at Intel. So I'll say the negative thing about Intel. I did not see that exact thing happen in Intel, but I did see it a startup with, like I said, 20, 30 people.
And this is what time frame?
This is 2017 or something like that.
People who, because I grew, my early career was spent in really big environments, the phone company literally, and then, quickly moved on, fairly quickly, but I was there for a number of years, but, early on moved to a pure startup. And I had the same experience you're describing, like, oh my gosh, I'm working with a small group of people and we're doing so much so quickly, with, so little oversight. And then you realize how much advantage you are in the environment relative to these behemoths.
Yeah.
But they don't realize it. They have no idea. It's so easy to underestimate.
Process is great for when you want to have certainty that what you are doing is exactly the right thing. But when you don't have that certainty and you just want to move as fast as possible, process is not necessarily the way to go.
Exactly.
But yeah, I think about the scale at which we started when I was at Rigetti and when I left, so much changed so quickly, and I think that was because it was a really dynamic environment, really great people. I think all those people, there are still people there. I don't actually know that many people more now at Rigetti, but they're all throughout the quantum industry. I know people from Rigetti who are at Google. I know people from Rigetti at IBM. I know people who are Rigetti. Name a company and they're there. But generally speaking, like it was a great experience. But around that time, a few things started to happen. So one was that I think I started to see the challenges of
because they were doing the
qubits.
Superconducting.
Yeah. I started to see the challenges.
They were and still are doing.
They were and still are. Yeah.
I
started to see those challenges, and I started to honestly use the lens of having been at Intel and seeing what they could fab and what they couldn't fab, and started questioning the kind of end goal that we were getting towards. I think we were putting a lot of faith in far-flung future things that I wasn't so certain of. And I would say when I left, there was, again, on the positive side, this amazing resurgence of what you could do with single neutral atoms. So when I had left neutral atoms research in 2013, 2014, there was a few different academic groups doing things with single atoms, but it wasn't anything like even what it was going on in 2017, 2018. And around that time, it just became apparent that while these things weren't quantum computers, because they were not at that point quantum computers, they weren't even barely qubits, it seemed like there was a really clear path forward to take the stuff I had done even as a grad student, the stuff I had done at Rigetti, not so much the stuff I had done at Intel, but the stuff I had done at those two places, and say, look, if you combine this with all this new work, I think there's something really amazing here. And when I looked around, it wasn't my initial intention to go start a company. When I looked around, there was just no one building neutral atom quantum computers. They weren't doing it at national labs. They weren't honestly even doing it in academia. I think you can flash forward to today where there's multiple different neutral atom quantum computing companies. There's more neutral atom like academic groups than I have any clue how it's possible. Like I went to 2 years ago, I went to a conference that essentially had none years before. And now it was like, there were like 60 or 70 groups across the world starting neutral atom quantum computing projects. It is astonishing. And I think
but as far as companies that are actually, making quantum computers, I'm not talking about maybe some two guys in the garage, but ones who've been doing it for a while that have made significant progress. It's a small number. It's less than 10 globally, right?
Yeah, I mean, I think if you look at the world's like top quantum computing companies, I think you're right. There's only, I mean, we could pick a number, but I think there's probably ways in which we could say whether they've made revenue, whether they've done demonstrations of this, that, or the other thing. I bet you're right. It's like 10 or something across the entire world. So it's a really small field.
They're doing neutral atoms.
Oh, sorry. Doing neutral atoms, I think it's even smaller. So neutral atom companies, it might be, I think, I counted the other day, it might be like 7 or something if you count the ones that are really quiet, because there are a few that exist now that have had the PR when they announced that they were being created, and then they got really quiet after they raised their first round, so they're going and doing whatever they're doing. But yeah, I think also just across the entire industry, though, I would go back and say there aren't that many quantum computing hardware companies in the world that are doing more than just toy stuff, and I think that number is also probably 10 across all the modalities. Or
really?
Like
that I would.
Yeah, I think if you look at like where people are and what they've accomplished, I think that you could draw very clear lines and say, well, if so-and-so hasn't done this, that, or the other thing, then they're still, let's call them pretty early. And then people who go beyond that line, it's probably like on the order of 10 or less.
Gotcha.
I mean, part of that is I'm also not counting like, if you discount Amazon, Google, Microsoft.
It's good to discount those companies. They're not big deals.
But I think that I think that what they're doing is they're spending a little bit of money, which makes a lot of sense, and getting a huge amount of marketing from it. And for Google, I mean, let's be honest, that's been a huge boon. They had their New York Times article about Willow, and I think their market cap went up like ridiculous, like $300 billion in a day and a half after that, or within hours, I think it was.
And Willow's superconducting.
Yeah, Willow's superconducting. Right? Yeah. So, I mean, I think that, part of the exciting thing around quantum computing is that these big companies are interested. And I don't even necessarily know, like I said, if those big companies really care about what kind of hardware they use versus making sure they control that scarce resource and also access that application space. And so I think that what they're doing now is really putting money on like internal projects where they think, oh, if this works out, that's great. But in the grand scheme of things, the amount of money that Google spends on its quantum computing division is nothing compared to what they spend on other divisions in any stretch of the imagination. So I think it's a kind of wait and see kind of approach. And like they've started putting money in other qubit modalities and stuff like that. So I think it's I don't know, everyone's trying everything because the end goal is pretty awesome.
And IBM, which has traditionally been super conducting as well, are they starting to look at other approaches?
They've announced some like partnerships with a neutral atom company, like a European neutral atom company. I don't know how serious that partnership is. But from the outside, I don't think they've done many other partnerships with other modalities before. So maybe they are serious about it. So.
Yep. Okay, so where were we at? So you were...
Oh, yeah, sorry.
You were breaking off to start up a neutral atom.
Yeah, so I broke off to start. I just became convinced, given where the technology was at, there were no other companies. And so I decided, I'll try this I think I did talked with my wife and said, I'm going to go start pitching. And if it doesn't work out, it doesn't work out, but whatever. But yeah, we started pitching, or I started pitching. I found
Did you have a partner at that point?
No, not when I started. I found a co-founder about 3 months in, and he had been just finishing up his work as a postdoc in Berkeley, and he kind of came at things not like from more of a not quantum computing side, but more of a chemistry kind of, also like experimentalist though, physical chemistry kind of side of things. And we started going out pitching together, and I would say that within have to remember, it's been a while now, but it was like 4 months or so. We started getting, soft commitments. And within 6 months, we had found a lead for a small seed. We then got the seed money. I think that closed in like within 6 months of starting the company. And then just like a month or two after that, we got NSF money. And then we started hiring and
You're in what year now?
this is in 2018, close to
Okay.
2019 is probably when we started doing a lot of our initial hiring and started getting a facility and started building our first system. And then from there we bought, we didn't buy, I think we started seeing our first, everything, all the dates come kind of jumbled, but I think we saw our first like neutral atoms, in like single neutral atoms in like March or April of 2019. And then from there, I don't remember when we first saw the qubit, so that we tried a new kind of qubit that has, very, very nice properties for storing quantum information, like really long, like 1,000 times longer than some comparable technologies, even among neutral atoms, let alone the 1,000,000 times longer compared to superconducting qubits. But we saw that qubit maybe the end of 2019, and I think around then was when we started raising. That's right, because we raised right before COVID. So we raised a Series A right before COVID, which was well timed, I guess, because it was right before COVID. And I think then we were able to go a little bit heads down and keep building. And around that time, as we were approaching Series B, that's when we started thinking, well, we need to raise much larger round. I'll still say rounds for quantum computing companies were not as large back then, but in our minds, we're raising a larger round.
And I think I came in as part of
I think
part
it was
of the Series A,
yeah.
but it was later after you did it. It was
Yeah.
maybe 9 months
Yeah.
later, a year later, with not a big enough check as I look back on it, but certainly got in there pretty early,
Yeah.
and then came in again more recently.
Yeah, and so we raised. So what we did is, as we started really expanding, and we had our first generation system going, where that was proving out a lot of the initial stuff, and that's actually the first system that actually ever had people on it external to Atom. I'll say Microsoft was on it. I don't know if there's others who were also on it, but I don't know if I'm supposed to say who. But Microsoft was on that system. That was actually how it was hilarious. That was actually one of the amazing ways in which we had our first interactions with Microsoft. Was they were one of the first people really to log in and use that system. And we at the same time had been building for almost a year and a half our next generation systems in Boulder. So we had our first generation system in Berkeley, our next generation systems in Boulder, because we wanted to expand to a much larger space. And Boulder is, like we were saying, this amazing hub for talent. And so we essentially had them run on the first generation system, but we were saying, look, everything you're talking about, we're gonna do on our second generation systems, which didn't exist yet. They kind of existed, but didn't have all the bells and whistles they needed to be a full quantum computer at that point. And then within months, they were then running on the second generation system. And that was when we had, by the end of 24, we had, like I said, Satya Nadella saying the words atom computing, which is pretty crazy.
Yeah, real crazy. So let's talk about valuations of quantum computing companies.
Okay.
So IonQ, which
Yeah.
has a similar kind of time frame as you had,
They're actually a few years earlier than us.
they're a few years earlier getting
yeah.
started, and they snuck out to be a public company via D-SPAC, right?
Yeah.
And became a very successful D-SPAC, and are now in the public markets worth close to $13 billion. I mean, it's crazy. Yeah. You have Quantinium kind of here in the Boulder area, between Boulder and Denver. They're a spin-off from Honeywell, but also they combined with
Cambridge Quantum,
Cambridge Quantum, and they're private, but they're said to be, valued based on external money in the many billions of dollars. So whether it's 5, 10, more than 10, that's still kind of playing out.
Yeah.
You mentioned a couple of the other, more, I'll say, older quantum computing companies, including Rigetti, that
and
also
even D-Wave, D-Wave is
D-Wave.
now trading quite high.
yeah, they're in the billions, both of them, maybe even 5, 6, 7 billion, even though they're
5 billion for D-Wave.
5 billion. I mean, these are big numbers. And then you hear Sandbox AQ, which has a history as being originally part of Google, got spun out,
Yeah.
focused, I think, more on applications than on the hardware itself. But they've been raising money in the many billions of dollars as a private company as well.
Yeah.
So you're seeing a lot of data points, none of which existed 3 years ago,
Yeah.
of quantum companies, most of which are focused on computing, that are worth billions of dollars.
Yeah.
How do you get your head around that at this early stage of quantum, when we haven't even gotten to the point where a quantum computer, quote unquote, works to do something that is special?
Yeah, I mean, I think it is funny. So we have a large hurdle to get over to build a working quantum computer, which is that we have to do better than any classical computer.
Yeah. Oh, by the way, I forgot PsiQuantum,
yeah.
another one with a
8, 9 or something like that.
extreme path forward in order to create a quantum computer that's also worth in the many billions of dollars.
Yeah. I mean, I think that people understand a few things, which is that, one, it's going to take a lot of capital to build systems that can outperform classical computers. So I think that's partly driving the valuation out of necessity. It does raise the bar for what you have to do to be successful, which is both good and scary at the same time. I think that it goes back to understanding if that value is real or not for some of the public companies. Like, we started talking at the beginning of this about Jensen Huang and the comments he made, which he then walked back later on. But like, the comments he made caused all of those valuations to cut in half, like in like hours or something ridiculous like that, or maybe it's days.
And now they've more than doubled since then.
They've more than doubled since then. But like, at the same time, like, I think let's be honest, like, if those valuations were exactly accurate, that should have been impossible. Like, if they were trading based off of multiple of revenue, then it should have not been possible for them to fluctuate that wildly. But at the same time, I think the markets we're going after are gigantic. And I think that is the fundamental challenge, which is we need a lot of capital to go and build what we want to build. And yet at the same time, the problems we're talking about trying to solve are not small problems. They are gigantic problems, which I think my argument is people are going to want to, well, I don't know if they're going to want to, but people will one way or another pay hundreds of millions of dollars or billions of dollars to quantum computing companies to solve their problems. Now, I don't think it's going to cost $100 million to run the quantum computer. So I think you really have to go and figure out how do you get to that, value of the solution, like I was talking about, and figure out, how to convince a catalyst company to do some kind of revenue share or something like that for time on that quantum computer. But I think that is what is driving the valuations up. Now, I think in the private markets, it's a combination of, what have we been able to do so far in terms of sales, or even like not even us, but like what have others been able to do with sales? And I think there have already been deals at the kind of like, now they're really complicated deals, but they're already deals at the like many hundreds of millions of dollars. You look at what
talking about commercial deals.
Yeah. And you look at what IBM has done. Like, IBM announces big deals after big deals, and they're claiming that they can sign deals now at the kind of $120 million kind of scale. And I think part of that is, again, for an IBM, it's probably a combination of many different things that are coming into that. But now with us partnered with Microsoft, I think there's many, many different things coming into these deals around what is actually getting promised to companies and what can they do, and how does the larger companies interact and handhold with the customers and stuff like that, or the partners. I think that it's a big market, and I think that the anticipation is that these things are just going to become more and more common. And honestly, like I was always a little skeptical of that, but I now have this example, which is, the money spent on quantum computing is going up. And my example now is, Novo Nordisk Foundation and IFO didn't put any money, or the state of Denmark didn't put any money in commercial quantum computing until they just signed two different contracts with Microsoft and Atom Computing. And I think there's going to be more places that do that. And I think generally speaking, there's a lot of interest for these deals. And I think that's just the beginning. Like, this is just the early stages of quantum computing. And of course, one of the things we have to compete with is, or not compete, but, a cautionary tale is the old, like, big supercomputing companies. and not recreating the mistakes that led to their demise. Like no one buys Craze anymore or whatever. But I think that's the path we want to go towards, is figuring out how to build these giant supercomputers that, I say giant in the kinds of problems they can actually tackle. For us, it's not even giant in physical size, but those are the kinds of things we want to build, and those are the customers that we want to get to, is people who want to do these big compute problems. And I think there's a lot of money in that.
Yeah, no question. I mean, when and how is going to be a lingering question.
Yeah.
When are we going to start really seeing examples of very valuable problems being solved and then commercialized? But as you alluded to earlier, you think it's using your computer. You think you're going to see that within the next 4 years, if I understood you correctly.
I mean, I think 2030 we will be displacing HPC for very sciencey problems, but I mean, sciencey problems that the U.S. government is super interested in solving for various national security reasons. But I think that soon thereafter, we'll take many of those units and hook them together with our own networking technology. And I think we're really off to the races, where we're not just replacing HPC because it was cheaper, better, faster, but we are accessing problems that are just.
Can you give us other categories of problems outside of the categories we talked about earlier?
Yeah, I think
you're excited about.
Yeah, I mean, I'm excited about a lot of the problems that I think people tried to run on NISC. Like, I actually think that there's the exponential advantage problems, and when we go and try to carefully say exactly what we're going to build, those are the ones we say, look, we have the algorithm, we know how to compile it, we know how to lay it out over across multiple modules and so on. We know it's going to take this long to compute. This is when you get the bit string. This is how many times you need to run it, so on and so forth. So there's these materials and chemical problems like that. But if I go back and think about all the things that people have tried since, say, 2016 to run on near-term quantum computers, I think all those things are actually going to be successful on utility-scale quantum computers. Like the challenge with,
such
running,
as
like all these optimization problems, like people talk about.
Optimization problems sounds boring.
Logistics,
and not as good.
Well, I mean, logistics problems, like how do you, take a bunch of different UPS trucks and figure out what is the most efficient way to
boring,
route them.
maybe valuable, boring. Give me something that is colorful.
I mean, I think what's colorful about them is the amount of money that's involved in them. Like how much gas money gets spent by
you are an entrepreneur also. Damn capitalist.
Well, no. I think the colorful and amazing things.
Think of drones and think of...
Yeah. I mean, I think there's lots of things like that. I mean, people... Actually, I visited a national lab where... I didn't sign an NDA or anything, where they were talking about like creating quantum networks on drones. And so they showed us how they were going to do that. And they showed us the drone it was going to get carried on. So there's some really wild out there things you can do once you put these things at the edge. I don't know if I want to build that, but I all the power to them. But I think that I think the biggest amazing things really do come into these materials and chemistry problems. I think, though, that if you go back to, again, all these like heuristic problems, optimization problems that people just kept slamming their head into for 2016 to now on IBM systems, on Rigetti systems, on, you name the system that you want to run it on right now, all those things become supercharged when your quantum computer is better. Mm-hmm. Like if you start to see signal from those things right now and someone says, I have quantum advantage. Right now, I kind of hem and haw every time they say that. But in the back of my mind, what I think is, oh my God, that algorithm, if it's showing any hint of quantum advantage right now, will be amazing when we can do a circuit 1 million times deeper or 10 to the 8 times deeper, like 100 million times deeper. And I think that's where you're actually going to see quantum computers get used in the very, very beginning by industry, is like, oh, look at all these amazing things that we tried to get to run on these non-error corrected quantum computers. And maybe we saw a hint and we got the right answer, but blah, 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 blah. All of a sudden, like 2, 3, 4 years from now, you're going to see those same things being run on error corrected logical qubits. And people are going to have their jaws dropping and being like, oh my God, we need to actually have this inside our cloud and part of our normal day-to-day operations.
Yeah. And I think just like the internet created things that we could not have envisioned when we were first talking about the internet. We talked earlier about the inherent limitation of Gen AI, that it's just taking today's data, getting really good at making sense of it and being able to use that to predict, just the most likely thing you should do or say next. But when you take that and say, okay, now it also has the ability to work with, QPUs, with quantum.
Yeah.
And so it's not going to be limited by just,
What the
taking
data that
today's
exists.
data and figure out. It's going to be able to say, and I need to discover something so that I could make more sense of this problem I'm trying to solve. And those two start kind of feeding off each other.
Yeah.
That's when there could be just impossible to predict outcomes that come out, hopefully for the good, like all these.
Well, I think the first example of that is, and there's some papers in 2017 that talked about this that people have pointed me to a lot recently. These papers came out of Microsoft, which is essentially how do you teach a quantum computer, and they don't quite put it in this language, teach a classical computer to be kind of a poor quantum computer. And I think that's a great example of what you're saying, which is they're like, well, first of all, you need the data. You need a way of teaching a quantum computer, or I keep saying it wrong, teaching a classical computer, what are the outputs of these kinds of circuits? And you need something, especially for really deep, complicated circuits, you need a quantum computer to supply that data for you. So I'm happy in that sense, because I'm happy to supply data to people who want to buy time on quantum computers. But I also think these things are going to be really useful, again, in understanding what actually needs to get run on a quantum computer versus what could get run piecemeal on a quantum computer and a GPU, or piecemeal on a quantum computer and a CPU. And I think that is the kind of way of the future, is AI really understanding, all things like this need to get run on a quantum computer for, because it's faster, better, cheaper, whatever. And I do think that's the way AI is actually going to get used in these systems. And part of that is, like you just said, it's teaching an AI about a quantum computer and what quantum computers can do and what they can't do. And I'm excited about that. I mean, I don't think it's taking anything away from a quantum computer. I think it's expanding what quantum computers can do and what they're going to be useful for.
Yeah, and including asking, a hybrid quantum classical computer to invent new things. I want you to really invent something new. I want you to discover that new material, discover that new drug, and for it to, take your characteristics and come up with kind of, here's the formula. And it will have to rely on both, quantum for part of that and Gen AI for other parts of it. And all of a sudden it's telling us how to create things, and maybe even combined with robotics, creating it in ways that, we're going to be like, holy shit, what's going on in our world?
Yeah. I mean, I think this all starts with just closing the loop with classical computers right now, which again, like that is what like a lot of such agentic AI is about, which is like, it really is like closing the loop. I mean, sometimes you have a human involved in it throughout that process, but you're closing the loop where you're saying, go do this thing, and it goes and does it. And maybe you have to have multiple loops inside where you're saying, okay, but go do this thing so that, achieves this speed up or something in this piece of code. I think it's exactly like you're saying. There will be a time where someone says, I need this material, it needs these properties. Please figure out what kind of material, try out, a variety of these kinds of metallic oxides, or, what it's going to say, try this out. And it's going to say, okay, well, what should I do? I should create these simulations that are going to tell me about the properties of material. Some of those are going to be HPC. Some of those are going to be run on a QPU. And it's going to run in that closed loop. And at the end output of it is going to say, okay, here's your material. And if robots, I guess, are involved, it'll go create them.
Yeah, how about it? Well, great, Ben. This has been fascinating. I've known you now for about 5 years, and learned a lot along the way. I feel like I'm learning a lot more from you in the last year or two than I've learned prior to that altogether. And love the way you've been able to transition from being kind of the founder, the singular founder, to CTO that started to build a team, to not being the CEO, to return to be the CEO and taking this company to without question, one of the absolute global leaders in building kind of a scale working functional quantum computer, and right here in our backyard in Boulder. It's an honor to.
Well, until we ship it out to Copenhagen.
Well, the shipping it to Copenhagen will hopefully be followed by shipping another one
here
in the U.S. and another one to Asia and all that stuff. So thank you so much for being part of this and for letting me and Cruise Ventures be a tiny part of your journey.
Yeah, thank you.
Okay, thanks.
Bye.
Thank you for listening to this episode of The Bear Roars. If you enjoyed the episode, please like and subscribe on your listening platform. This podcast was produced by Loud Bear Productions and edited by Kendall Weinberg with support from Gibson Seeger, Katie McDonald and Elise Pettigrew.